Okay, so you're familiar with the two types of cell survival curves, the populations that they represent, the number of targets related to each cell type, whether it graphs as a exponential with one target or a sigmoidal with multiple targets, and also how to calculate D sub Q. So now we're going to look at some additional factors that influence the shape of the cell survival curve. We're going to start with radiosensitivity, then we'll look at target number, and if we get to it today, we'll go into the oxygen effect and the remaining others on the list. We probably won't get that far today. But regardless, we have a whole nother class period to get through this information. So we're going to start first with radiosensitivity. And how would radiosensitivity affect the shape of the cell survival curve? Well, the first thing that we have to do is to define radiosensitivity relative to cell survival curves. Now, we all know what radiosensitivity is in general. When we think about radiosensitivity, it's simply how easily is something damaged by radiation. If we have radiosensitive cells, a little bit of radiation can kill them. If we have radioresistant cells, then it takes a lot more radiation to cause damage. But when we think of radiosensitivity in terms of cell survival curves, it has a very specific definition. And that definition is how much radiation it takes to inactivate a target. So with radiosensitivity and cell survival curves, we are quantifying the amount of radiation that it takes basically to kill a target. But it's a dose. That's what I want you to pay attention to. It is a dose. Just like D sub Q was a dose level, you had to say it's 150 rads or it's 60 rads. Radiosensitivity relative to cell survival curves is also a dose. It's the dose of radiation that it takes to kill a target or inactivate a target. You say, well, how much does it take? And the answer is, it depends. The radiosensitivity varies with cell type. And the radiosensitivity of the cell type varies according to the law of B and T. Can somebody tell me what two factors influence cell radiosensitivity according to B and T?
Wasn't it tissue differentiation?
Tissue differentiation. So which tissues are more radiosensitive? Those that are poorly differentiated or highly differentiated?
Poorly.
Poorly. So simple cells. All right. What was the other factor identified by the law of Bergenet and Tribandot?
Mitotic activity.
Mitotic activity. So which would be the most radiosensitive? A high mitotic activity or a low mitotic activity?
A high.
High. So cell types that are most radiosensitive have a high mitotic rate and they're poorly differentiated. So therefore, if we were using those cell types in cell survival curves compared to other cell types, they would be the most radiosensitive or the most easily damaged by radiation. Now, when we look at the cell survival curves, we can tell the most sensitive population simply by looking at the steepness of the slope of the straight line portion, or the steepness of the slope of the exponential portion, however you want to say it. If we look at this graph, and it is a little bit distorted, but here we have curve A. Curve A is exponential. Curves B, C, and D are all sigmoidal. Okay?
Sigmoidal.
So here's the straight line portion of A. Here's the straight line portion of B. Here's the straight line portion of C. They are all essentially parallel. They have the same slope. That means they are equally sensitive to radiation. But look at curve D. It's a sigmoidal, but its slope is very shallow. Since its slope is more shallow, it is not as sensitive to radiation. So whereas curve A, B, and C are equally sensitive, curve D, that population would be less sensitive. So we can get a general idea of radiosensitivity, and this is just a general idea. This is not quantifying radiosensitivity. This is just saying, hey, I can look at this and tell which is the most sensitive population.
We said A through C are all exponential, right?
No, only A is exponential. It's the only one that's a straight line. You see, this one has a shoulder, this one has a shoulder, this one has a shoulder. These
Gotcha.
are sigmoidal, but you look at the slope of the straight line or the exponential portion of the curves. Now for the exponential A, it's the whole line. The slope is constant. But for B, C, and D, you look beyond the curve to the straight line portion. Does that make sense?
So it has an exponential portion, but it's
Yes.
a sigmoidal line, correct?
Yes, it's a sigmoidal curve, but the third part of the sigmoidal curve is the exponential portion, which means it is a line.
Okay.
Okay? All right, so let's go back to your graphs for just a second. Pick up graph 1 and graph 3 again. Those are the first two that we dealt with. If we look at graph number 1, we have curves A, B, and C. Somebody tell me which of those is the most radiosensitive cell population?
A.
A, because it has the steepest slope. The line is going more sharply downward, okay?
Yep.
So
B and C would be equally, right?
no,
Oh.
look at them. The most steep slope is A. B is a little less steep, so it would be a little less radiosensitive. C is the broadest or the most shallow slope, so it is the least sensitive. They are only equally sensitive when the lines are parallel, or for exponentials, they'd have to be right on top of each other. Okay,
I got you.
so the more shallow the slope, the less sensitive the population. And for these,
So basically, only
Go ahead.
sigmoidal lines would be equally sensitive in retrospect, right?
they could be, yes, yes. All right, so let's look at curve number 3, or let's look at number 3, graph number 3. on graph number 1, it was pretty easy to tell which slope was the most steep, which was the most shallow. But here we have two curves. What do you think about them in terms of the slope of the straight line portion? Which is the most steep, which is the most shallow?
I think A is
B.
the most steep, and then B is more shallow because B is going more off to the right side.
I say the other way.
But
I
you
say
have to,
B.
but you have to be careful of that because you can't
B shallow.
shoulder. The shoulder sends it further to the right. Look only at the straight line portion. And
So B would be, I think, steeper.
I think that it's going to be close. I think they're pretty close. We're probably going to have to actually quantify radiosensitivity in order to get an exact answer, because these are pretty close. You know,
I don't know how to do that.
When you look at the straight line portion, they almost look a little parallel.
and so that's why they're close. In all honesty, I think that A is slightly steeper, but not by much. But that's hard to eyeball. And the only reason I wanted you to look at them was so that you would know, you know, most of the time you can tell just by looking, but sometimes it's too close to really tell. So you have to quantify radiosensitivity. But in general, just the general estimation of radiosensitivity is found by simply looking at the slope of the straight line portion. The steeper the slope, the more sensitive the population. The more shallow the slope, the less sensitive the population. But remember, radiosensitivity, when we relate it to cell survival curves, is a dose. So we have to be able to measure it or to quantify it. For exponential curves, we call it D sub 37, and I'll explain that in just a second. For sigmoidal curves, we call it D sub 0. So remember D sub Q, that was the quasi-threshold dose for sigmoidal curves. D sub 37 is a measure of radiosensitivity for exponential curves. D sub 0 is a measure of radiosensitivity for sigmoidal curves.
When you say quasi-threshold,
Yes, the threshold the threshold or quasi-threshold dose is D sub Q. That was what we looked at a little bit earlier.
but that's different from the radiosensitivity of it.
Yes, it is different. Quasi-threshold dose is measuring the width of the shoulder. Okay, so D sub 37. D sub 37 is the 37% dose slope. And it's defined as the dose that kills 63% of the cell population and 37% survives. It's the dose which will produce one hit per cell in the irradiated population. And you might say, why did they pick these numbers? Why didn't they just say the 50% dose slope? It's the dose that kills 50% and 50% lives. Well, it's based on random events. Radiation interacts at random. And when they study random events, basically, if you had 100 random events, 63 would go one way, 63% would go one way, 37% would go the other. So that's why they picked these numbers. There was a good description in a previous textbook that we used, and it said, if you went out into a flat field, like a football field, and you made a grid of 100 equal cells or 100 equal squares. So a grid of 10 squares wide by 10 squares long. And if you went up 100 feet and dropped 100 drops of water, on average, 63 of those 100 blocks would be hit.
We'll hit somebody.
And then 37 would be dry, because that's a random event. So that's just one example of why they chose these numbers. But anyway.
But Don,
Go ahead,
are you
Marcus,
gonna are you gonna show it, make an example of how you graphing this a little bit?
Yes, I'm going to show you exactly how. You just got to let me get there.
Okay. All right, cool. All
Okay,
right.
so D sub 37 is the dose at which 63% of the cells die and 37 survive. And it's very easy to determine. You find it by finding the dose associated with 37% survival. So I want you to get graph number 1. Okay, so we've already had graph number 1. We've talked about it multiple times. So with graph number 1, I'm going to stop sharing this, and I'm going to now share the whiteboard again. I'm going to erase this curve and draw a better one.
Oh, that one was so nice though, Don.
I know, you know, my drawing is just amazing, right? Not really.
Could have been an artist.
I should have been an artist. Well, God bless you.
I'd buy one of your drawings or paintings.
Okay, well, good. I'll sell you one. Okay, so here is my cell survival curve. Here is 100% survival, although my writing's pretty terrible. And this is an exponential, so it's a straight line. Okay, well, except to the end where I screwed it up. Oh, sorry.
I knew my ruler wasn't off.
All right. So to determine D sub 37, let's look at the y-axis. Okay, so here's the x-axis, and it's dose. Here's the y-axis, and it is surviving fraction, or percent survival. Okay, so where the curve begins, right here, that's 100% survival. As soon as we start to administer dose, cells start to die, and so the line starts to move downward. It has a negative slope. If we want to find the place where 37% survive, look down the y-axis. So everybody sees the 100 because that's where it starts. The 9 would then be 90, the 8 would be 80, and then it would be 70, 60, 50, 40, 30. Well, you have to find 37%. So somewhere down the axis between the 3 and the 4, you're going to find 37%. Okay. At 37%, you draw a line straight across to the curve. Where it intersects the curve, you drop the line straight down. That is D sub 37. Okay. So you have 3 exponential curves, A, B, and C. I want you to calculate D sub 37 for each one. Don't yell out your answers.
Quick question, Don.
Uh-huh.
Right at the bottom of the y-axis, you have 1, 2, 3. Would that represent 10, 20, 30?
No, no,
No.
because as you go down the cycle from 100 and then it gets down to 1, well, that 1 represents 10%. So the 9, 8, 7, 6, 5, 4, 3 below that is just literally 9%, 8%, 7%, etc.
Thank you.
Okay. All right. So has everybody got answers?
Ready.
You're ready. Okay. So let's.
All right.
So let's see. Jamile, what did you get for D sub 37 for curve A?
Woo.
700.
I'm
All
sorry,
right.
100.
100. All right. Did everybody get close to 100?
Woo.
Yeah.
On the
I hope
dot.
so. 100 rads. Don't forget, you got to have a unit. Okay, Marcus, what
100
did you
rads.
get for D sub 37 for curve B?
I have 190 rad.
All right. Very good.
I got 180.
Okay, look at, if you're off, but I mean, it's okay. There'll be a little bit of variance, but if you're off a little bit, that's okay. I think my estimation was 188 on this one. So very close. All right. Shamarva, what did you get for D sub 37 for curve C?
I got 290 rads.
All right, 200
Woo!
rads. So hopefully the rest of you got somewhere in this ballpark, because these are very close to what my answers. So these are correct. So it's pretty easy. You just have to remember that D sub 37 is a measure of radio sensitivity. So which cell population, the cell population for A, for B, or for C, is most radio sensitive?
C.
Which is most
Which is
C,
most
yes.
radio sensitive.
C.
Oh, A.
A is C is most C.
Resistant.
C is
C
the
can,
most
yeah,
resistant.
resistant.
Look at the
Oh, yeah, the steepest slope, that's A. My
Look
bad.
at the graph. The steepest slope is A. So just in general, A should have the lowest D sub 37, because in a sensitive population, it takes less radiation to kill a target. So curve A had the lowest D sub 37, indicating it's the most sensitive. Does that match our general observation? Yes, it does.
Yes.
We said curve C would be most resistant. It has the most shallow slope. The D sub 37 that we calculated is 290 rads. So that makes sense. The more sensitive the population, the lower the D sub 37. Okay. All right, let's do one more. Take curves number 3 or graph number 3 and calculate D sub 37 for curve A.
Curve.
Because remember, D sub 37 applies to exponential only. So D sub 37 for curve A.
Ready?
Okay.
I'm ready for graph number 5 now.
Is everybody else finished?
Yes.
Okay. So what was your answer? What would you get for D sub 37 for curve A?
185 rads.
170.
I got 175.
I got 170.
All right, let's look
170.
again. We're getting a pretty broad range here.
Yeah, I got 240, so
1, 2, 3, 4, 5, 6, 7. I got about 185 to 188.
I go with the most I can go with is 175.
No, I think you're a little low. Check to make
Ain't not that type of
All
sound.
right,
Maybe
37.
180.
Yeah, maybe 180. I don't know. 188 seems a
Maybe
little
180.
high, Don.
Yeah, that's
Yeah.
a little high, Don.
Well, check
Don, I
to
think you need to check
make
your
sure
line.
that you're on 37%.
Your ruler.
The two most common errors is that you're not actually on 30.
Are you sure you're not using a highlighter, Don?
I'm not using a highlighter. You could be on like 38 or 36 by mistake. The other thing is that when you drop the vertical line, it may not be straight down. It may be leaning to one side or the other. So be careful of that. But yeah, I got 185 both times, somewhere in that range.
Are you sure you're on 37?
I am. I
We
checked.
sure. We found out together.
I don't know.
I
I
checked.
can go with 180. I can go with 180, Don. That's as high as I can go.
All right. Well, I might count yours wrong just for meanness.
I don't know, Don.
All right, wait. I mean, I can go 185. I can actually go. I can go
okay.
185.
Don, can I see your graph just to make sure I graphed it right?
I mean, it's just basically, can you see that?
But I feel like I want to stand behind this 180, Don.
I don't
But I can-
know.
I gotta stand at 175. I mean, I don't think I can budge.
Nah, I'll go
Oh,
180.
well,
I
you
can go
just
180.
remember, I have the,
Who's grading?
so
Yeah.
I have the
Oh,
grade
no.
book.
It was fun while it lasted, Chad. All right?
Let's do this. Let's take about a 5-minute break.
Do one more.
At this a while. No, let's take about a 5-minute break, and then we will come back and go do just one more thing, and then we will hear Rosemary's Feature Kucha.
Hi, Ivy's dog.
Okay. All right. So we are going to look at how we measure radio sensitivity for a sigmoidal population. So we know to quantify radio sensitivity for an exponential cell survival curve, we use D sub 37. To quantify radio sensitivity for a sigmoidal population, we use D sub 0. Now, D sub 0 is called the mean lethal dose. And like I said, it's essentially the same thing as D sub 37. We are trying to quantify radio sensitivity of a sigmoidal cell population. In order to do that, we have to work on the exponential or straight line portion of the curve. The slope of a sigmoidal cell survival curve is not constant. So it won't work if we try to do it on an upper portion of the curve. So we always have to make this determination on the straight line portion. So here's what you have to do. You have to designate a 100% and a 37% on the exponential portion of the curve. You find the dose associated with each, and then you subtract to get the difference. And the difference is D sub 0. So everybody get graph number 4. Okay. And on graph number 4, we're going to be looking at curve B because that's the sigmoidal. If you look down the y-axis, you see where the curves begin. That's 100% survival, and it goes all the way from 100% down to 10% and then down to 1%. What you need to do is designate 10% as 100%. And you can just write it in parentheses beside that. And that's what they're doing here. They're designating 10% as 100%. They draw a line straight across to the curve. Here, for some reason, their dose axis is upward. So they went upward to cross the dose axis. For us, we're going to draw a line across to the curve, drop a vertical line downward to the dose axis to get a dose level. Okay? So does everybody have that number?
I'm doing that for curve B, correct?
For curve B.
Wait a minute, Don. I need you to put your whiteboard. Why don't you put your...
Okay, I will in just a second. I'll try.
Where's your whiteboard at?
Yeah, I'll show it to you in just a second. Anyway, designated a 100% across to the dose axis, drop down, find the dose level. Then a designated 37% across to the dose axis and drop down. So I'll stop this. I'll go to the whiteboard and share it. Okay. So here's my axis. Here is my sigmoidal curve. Oh, that one's pretty terrible, but okay. So this is,
But do your numbers though. What are your numbers on the side?
I'm about to get there. Here is 100% survival. That's where the curve starts. So then there's going to be 9, 8, 7, 6, 5, 4, and somewhere down here, there's going to be 0.1 or just another 1, but it would be 10%. We're going to designate that 10% as our 100%. We're going to draw a line straight across until it hits the curve. And we're going to drop a line straight down until it crosses the dose axis. I just refer to this as the dose at 100. That's my designated dose at 100. Okay. Then I'm going to go further down from 1 until I get to it's going to be 0.037. Okay. Or my designated 37%. Okay. I'm going to draw a line straight
So
across.
you went
Well, wait a minute.
down instead of uh-oh.
They went up because they put their dose axis. It's not going to let me erase. Never mind. All right. So at 37, you do the same thing. If I could draw a straight line, draw a straight line straight across, drop it down. That is your dose. At 37. So you've got two dose levels. Okay. So for the dose at 100, what did you get?
149
Okay, 149. We'll go with that.
rads.
And you 149 rads. All right. What's the dose at your designated 37%?
Yeah, I ain't.
179.
Okay, 179. Anybody else get
Yeah,
anything
I ain't
different?
get you. Let me see. Yeah, I got for the I got one. Oh, well, I guess I got 110. Oh, I guess I'm right. Okay, same thing. I guess yeah.
In the range, so.
Okay. Okay. I got just a little bit higher, but that's all right. We'll go with 179. Okay, just for illustration purposes. So D sub 0. Oh, come on, let me talk. D sub 0 is equal to the dose at 37 minus your dose
I got 180.
at
Yeah, I
100.
got
That's close
185.
enough. It's a ballpark. Okay. So in this case, the dose at 37 was 179 rads. The dose at 100 was 149. So the difference is what?
30.
30.
Exactly. So D sub 0 equals, in this case,
149 rads.
30 rads. So if you're somewhere in that ballpark,
Yeah, because I got 150 and 180. I still got 30 rads. I see what you're
exactly. So it's an estimation. Here's the thing. For sigmoidal curves, because the slope is constant, is not constant, excuse me, that's why you have to come down to the straight line portion. You can only estimate radiosensitivity if there's one target. And on the exponential, there's one target left. Okay? So you have to be on that straight line or exponential portion where there's only one target left in order to estimate radiosensitivity. And D sub 0 is in essence exactly the same thing as D sub 37 for an exponential curve. It's the amount of radiation that it takes to kill one target. So in this example, it was 30 rads. Okay. All right, so we are going to stop here today, and I am going to make Rosemary our host so that she can show us her Picha Kucha presentation.
Yay, go Roll! Woohoo!
So Rosemary, you are now a co-host, so you can open your presentation and start it, or share your screen and start your presentation. Do you have that option now?
Quick question, Don, do we just take notes?
Yes, you will need to take notes. The Pecha Kucha presentations that are occurring now will be tested on the next test. Those that fall in the next test range, you'll be tested on them with the subsequent test.
On.